Welcome to the math record. Today I'll be introducing the idea of inverse derivatives. For this video, I'll only be covering the general idea how to calculate them. Afterwards, in the next two videos, I'll cover more specific inverse derivatives, like the inverse trigonometric derivatives and the logarithmic derivative, which is just the inverse exponential. So if you don't know, what is an inverse function? Well, basically, if we have a function f of x, right, y equals f of x, then let's say we plug in x is equal to 1 and the y comes out as like 2. Then we're going to have an inverse function, whereas y inverse of f of x. That means we're going to switch the x and y's. That means if we plug in x is equal to 2, then y comes out as 1. So plug in 1, get 2, plug in 2, get 1. So it just switches that. Okay, so now we're going to find the derivative. So to do that, we're going to use a property of inverse functions such that f composited with its inverse function is equal to x. And to find the derivative, we're going to have to do the chain rule. So the derivative on the left side is the derivative of our function composited with our inverse function multiplied by our function side because it's composited, so we have to use the chain rule. So the derivative of our inverse function. And then the derivative on the right side, the derivative of x is 1. So we want this, the inverse of our the derivative of our inverse function. Okay, and that's equal to 1 divided by this function. So the inverse of our the derivative of our inverse function composited with our inverse derivative. Okay, so this seems like a handful, so let's just try an example. So let's say we have a function f of x, and let's say that is 2x cubed plus 1. And let's say you want to find the inverse derivative at 17. Okay, so inverse derivative at 17. So plugging it into this formula, we have 1 divided by the derivative of our function, inverse derivative of 17. So how do we find that value? Because we actually don't have the function for our inverse function. So what we could do is that, as I said before, they switch their x and y values. So the x value, which is 17 for our inverse, is actually the y value of our original function. So that means 17 is equal to 2x cubed plus 1. So 17 minus 1 is 16. 16 divided by this 2 is 8. That means x is equal to 2. So we could substitute that back in. So 1 over the derivative of our original function at 2. Well, we could find the derivative of this pretty easily. So the derivative is equal to the derivative of 2x cubed is 3 times 2 is 6, and then 3 minus 1 is 2, and derivative of constant is 0, so we don't have to worry about it. Now we plug in 2 in here. 2 squared is 4, 6 times 4 is 24. So that means our derivative is 1 over 24, or basically the slope at 17 for our inverse function is 1 over 24. Okay, so that's just one of the equations. So it tells us that we could find the derivative of our inverse without actually finding the function of our inverse derivative. So another thing we could do is that we could actually find the derivative of our original function using just the inverse. So we just had to use a different formula for our inverse, which is the inverse derivative composited with its irregular is equal to x. So doing the same process again. So the derivative of our inverse composited with its original multiplied by whatever inside because we need to chain it. So the derivative of our function is equal to the derivative of x, which is 1. That means our derivative of our original function is equal to 1 divided by the derivative of our inverse function composited with our original function. So let's try an example. So it's the same procedure. So the inverse, let's say our inverse function is x to the power 5 plus 3x, and we want to find the derivative of f at 4. So basically what we could do, as we did before, follow this formula. So that's 1 over the inverse function of f of x, the derivative. Sorry, forgot to put the 4. Okay, so we first need to find this. So we know that the x value of this function is actually the y value of this function. So we have 4 is equal to x to the power 5 plus 3x. So the same procedure. So this is pretty simple. That means x is equal to 1 because 1 to the power 5 is 1. 3 times 1 is 3. So 1 plus 3 is 4. So that will give us the inverse derivative of 1. So to find that, we need to find the derivative of this function. So derivative of x to the power 5 is 5x to the power 4. The derivative of 3x is 3. Plug in 1. 5 times 1 is 8. 5 times 1 is 5, plus 3 is 8. So that means this is 1 over 8. Or the derivative at our original function at x is equal to 4 is 1 over 8, which is also our slope. And that's basically how you do it. For both processes, it's basically the same. You're given a value and the function, and if you want to find the derivative of its inverse, set that value that you're given equal to our function, find that x value, and then find the derivative of the function, plug that x value in, right? Plug that x value in, and then do 1 over that number. And that's basically it. As stated earlier, I'll be using this process to find the derivative of inverse trigonometric functions and logarithmic functions in the next 2 videos. And I'll see you then.